Now let's look at the implementation and the correctness of our algorithm. So this algorithm is called hierarchical consensus because it orders the processes in hierarchy with a rank. It uses a best ever broadcast and a perfect failure detector P. And here is the initialization of each process. Detected is used to detect failed processes. The initial round is 1. There is no current proposal, and the last proposal adopted is 0. So here you store always the last adopted proposer and the last adopted proposer ID. Then each process has an array called broadcast with the elements equal to the number of processes, and delivered with elements equal the number of processes, and they are initially false. So these two arrays are Boolean arrays. So whenever you get a crash notification of PI, you add PI to the set of detected failed or crashed processes. And then here, if you get from the environment a propose event and you haven't done a proposal before, so this says that you don't have a proposal before, then you initialize your proposal to the value v. So this is basically to set the process's initial proposal unless it has already adopted another node's proposal. So this, and now you see what you can do if you are a leader. So if the round is equal to my rank and I did not broadcast any proposal, and I have a proposal value, this is important, then I do what I should do. So I'll trigger only once, as it's written here. I say I have broadcasted. I trigger a decide to my parent component, and I best ever broadcast my proposal that I have stored at this round and the round number. So this is clear. Now, when a process gets web broadcast delivery, it looks to the rank of the proposer, process R. And if R is higher than my last proposer, which is an invariant saying only adopt newer than what you have, then you can adopt this proposal number and this proposal value. See, the last proposal will be R, and the proposal value will be the value you got in the delivery of that message. And then you say that you have delivered. And if I have already delivered a message for that round, or I detected that the process of that round has crashed, I move to the next round. So observe that this algorithm goes in rounds, but it is completely asynchronous. It is the message causality that causes this round, as if it was like going from one round in a synchronous way to a next round. So let us look at the correctness of the algorithm. Validity says that I can only decide on one of the proposed values. And as you can see from the algorithm, you decide your own proposal or you adopt a value from some other proposer. Integrity, which says you decide only once, and this is true because the rounds increases monotonically, and a process only decides once when it is the leader of the round. Termination is guaranteed because every correct process makes it to the round when it is leader, and when it is leader it will decide. And how is that? If some previous leader fails by the completeness of the failure detector, it moves to the next round, so it ensures progress. But if a leader of some previous round is correct by the validity of the best ever broadcast, it will get a delivery and then moves to the next round. Now let us look to agreement, which says no two correct processes decide differently. And this is quite easy. As we said before, it is based on the idea of this algorithm. You take the correct leader with the minimum ID. Because we have ensured termination, then this process, in this case it is process Pi, will decide on value V. And this is the first leader that is correct, and it decides on the value V. It will best ever broadcast the value V. Every correct process gets V and adopts the value. And we know that no older proposals can override this adoption because we do not accept all the proposals. And all future proposal and decision will be then V. So how many node failures this algorithm tolerate? We are in the fail stop model, and this algorithm in fact tolerate up to n-1 process failure and still works.